Hi, and welcome to our video on flying a teardrop procedure turn. And we're going to do this at Gomel in Belarus, Uniform Mike Golf Golf runway 28. But before we get started, we'll be doing a little bit of math, very helpful in preparing for a teardrop procedure turn. But if you understand this little gag, you may want to skip the next few slides because you probably understand what I'm about to say anyway. First, I'll cover a rule of thumb, the 60-to-1 rule. It's a rule of thumb because it's an approximation. The approximation makes the math a little easier to do in your head. But I'll say there's nothing wrong with having a calculator out when you're getting ready for a flight. You can make a note of your results and you don't have to worry about calculating things in your head. But the 60-to-1 rule says that at a 60 nautical mile distance from a point, a 1-degree angle turned around that point has a distance of 1 nautical mile between that 1-degree angle. If you were 6 nautical miles away from a point and turned 1 degree, it would be a tenth of that, 6 being a tenth of 60, so that would be 1/10 of a nautical mile for each degree you cross. So to apply the 60-to-1 rule, we have the distance across an angle equals the distance from a reference point times the total angle crossed divided by 60. This works all the time, but we're going to apply the 60-to-1 rule here to the teardrop procedure turn itself. So here's our piece of our approach plate for UMGG. You see we fly out 10 nautical miles, make a teardrop turn, and fly back in, intercept the localizer, and land. What we'll need to find out here is the length of that red line, which is the diameter of the turn portion of the teardrop, and so we'll make that calculation. First thing we need to know, the distance from the reference point, and here it's shown on the chart at the turn point from the Homiel VOR D10.0, meaning 10.0 DME, and it's also indicated on the blue line up to the turn point. The next thing we'll need to know is the total angle crossed, and we find that by knowing our outbound radial of 083 degrees and our inbound heading on the localizer of 283 degrees. And the difference between 283 and 263 degrees is 20 degrees. Note that 83 is the reciprocal heading of 263, and that's what you'll need to have. And there's a quick rule of thumb for this. For headings under 180 degrees, add 20 to the first 2 digits, that gives you 28. Subtract 2, that gives you 26. The reciprocal is 263. And then finally we apply the formula. Distance across the angle equals the distance from the reference point times the angle crossed, 20 degrees, divided by 60. And that is represented by the red line, and that's 3.33 nautical miles when you do the math. Now what we'll actually be doing is turning around a radius point. So the radius of that turn is simply half of the diameter, or half of 3.33, which is 1.67 nautical miles. So some helpful rules of thumb before we get to our final calculations. And these rules of thumb hold well for true airspeeds between 90 and 180 knots. Pretty typical speeds for almost any aircraft for flying approach procedures. So the first rule of thumb is that the turn radius of a standard turn, this is a 2-minute turn, is 1/2 the true airspeed divided by 100 plus 0.05. For example, for 140 knots, half of 140 is 70, divided by 100 is 0.7, add 0.05, you get 0.75. For 160 knots, half of 160 is 80, divide by 100, add 0.05, 0.85. 0.8 plus 0.05 equals 0.85. For 175 knots, half of 175 is 88, sort of, and we'll divide by 100 and add 0.05 and get 0.93. Typically, when you encounter a 5, you'll want to go ahead and round up the halved 5. The half of that is 2.5, rounded up to 3. If you do that, then you'll find that this formula is slightly more accurate than if you round down. So I suggest making any 5s a round up to a 3. So that's your standard turn radius for, again, a 2-minute turn, calculated fairly simply. And remember that this is true all the time. It doesn't matter where you are, when it is, as long as your true airspeed is 160, your standard turn radius is 0.85. This is true for any aircraft, any time of year, any location in the world. It only depends on true airspeed. The bank angle for a standard turn, again standard turn being a 2-minute turn, is 0.15 times your true airspeed. Again, holds for any aircraft, anywhere in the world, only based on true airspeed. Easy way to do this, take 10% of the true airspeed, take half of that, and add it together. So 10% of 140 is 14, half of 14 is 7, 14 plus 7 is 21 degrees. For true airspeed of 170 knots, 10% of 170 is 17. Half of that is 8. Well, 8.5 we know. But we'll add 8 and 17 and get 25 degrees. And you can round up or round down as you like. The half a degree is not going to matter. There are a lot of other factors. In the first place, I don't think you will be able to hold an aircraft within a half a degree bank angle, and you'll always have winds to deal with and other factors. And finally, we'll apply these rules of thumb to determine the bank angle for a given turn radius. We'll define that given turn radius as r, which is equal to the radius of a standard turn divided by that turn radius times the bank angle for a standard turn. So we'll go back to our teardrop turn at UMGG. We've already calculated the turn radius at 1.67 nautical miles. We know we're flying out 10 miles, making a turn through a 20-degree angle, and that results in the 1.67 nautical mile turn radius. We're going to use 160 knots as our basis for calculation, but you'll find that when we actually fly this that we'll be making some adjustments. True airspeed halved divided by 100 plus 0.05 gives a standard turn radius of 0.85, as we saw before, and the bank angle for that speed 160 equals 16 plus 8 equals 24. So the bank angle required to fly the actual turn radius for the radius r of 1.67 nautical miles is 0.85 divided by 1.67 times 24 degrees. And 0.85 over 1.67 is just a hair more than 0.5. So we'll take half of our standard turn bank angle of 24 degrees, which gives us 12 degrees. Now all this is based on 160 knots, obviously, as shown above. But when you're flying with respect to a object on the ground, in this case the VOR for the teardrop procedure, true also for DME arcs and any other path defined by ground reference, you must consider the effect of wind. And we'll talk about that a little bit when we actually get into the procedure. So here we are, we're actually climbing out. We notice that wind is a factor. We've got a quartering tailwind, and it's fairly strong. You notice our actual heading of the aircraft is 128 degrees, but our track is 120 degrees. So about a 8 degree crab angle for this quartering tailwind, and it will be a factor all the way through our approach. So it'll make things interesting, to say the least. And take a look at the chart. I'll pop this up on the knee board. This is a handy little add-on if you haven't gotten it. This is something you might want to look at if you fly these approaches. Kind of review our approach again. Outbound on the 083 radial to the turn point at 10 nautical miles. We make the turn. Our sort of reference point is 160 knots and a 12 degree angle. Intercept the localizer, fly inbound as you would on a conventional approach. Verify your minimums, and also verify what your initial approach fix altitude is going to be. Our minimum safe altitude here is well below that. It's below 2,000 feet, but you'll notice that the initial approach fix altitude requirement is 4,000 feet. So we have to hit the initial approach fix at 4,000, even though the minimum safe circle shows that from the direction we're coming from, minimum safe is 1,800. So we'll cross the initial approach fix, the home MEAL VOR, at 4,000 feet, and descend down to our initial approach height after we finish the turn of 2100 feet. And this is where we'll fly until we intercept the glide slope. So we fly outbound for 10 nautical miles, make our turn, our teardrop turn, and again using as a initial basis our calculation based on 160 knots. But you'll find that due to other factors, including a significant tailwind, that our speed is going to be up and we'll have to contend with winds. So we'll adjust as we go. We've begun our descent. Again, our target altitude is the crossing altitude at the initial approach fix at the VOR. And we'll need to slow down a little bit as we get towards 10,000 feet to be below 250 knots. Notice we still have a significant tailwind, and we'll adjust our vertical speed to help us slow down to make sure we are below 250 knots once we get to 10,000 feet. Just to show you where we are on the map on Plan G, coming in from the northwest, and we will overfly the VOR, fly outbound on the 083 radial, do the teardrop turn, and come back and intercept the localizer. So here we are, we're leveling off. We're within just a few miles of the home EO VOR. Remember, crossing at 4,000 feet, the closest we're going to get is 4,000 feet away, DME wise. We'll be directly above it, 4,000 feet, which is about 2/3 of a mile. We have about 2/3 of a turn to make here from our current heading to the 083 heading, and we know at this speed that our turning radius is roughly a mile. So we're going to start our turn at about 1.25 miles or 1.5 miles out to intercept the 083 radial. This is standard procedure for crossing a VOR. We do have other videos on that if you are interested to learn a little bit more specifically on that. So we're crossing the VOR, and you'll notice here when we do cross that the cone of silence occurs right around 0.6 to 0.7 nautical miles. Here it comes back again, and we're at 0.7 now. That's because we overflew it at about 0.6 or 0.7 nautical miles above the VOR station, so that's as close as we're going to get DME wise. And we'll make the left turn gently out to 083 degrees. No need to be in a big hurry, and we do need to move a little to the left, but only a small angle is required because we're very close to the VOR and things do happen quickly, so you don't want to overshoot that. And as that comes back in, you'll notice that we have pretty much a pure tailwind at this point. It's running about 34 to 36 knots. We'll nudge over a little bit to the left and fly outbound on the 083 radial. And we've already set up for our initial approach configuration. We're going to lose some altitude now down to that 2100 foot level that we want to be at in the teardrop turn itself. So we'll begin our descent. Unfortunately, what we're going to run into here is, because of this fairly strong tailwind, is we're going to have a little higher speed than we anticipated. But that's okay. You know that you can approximate things in your head a little bit. The turning radius at 180 to 200 knots is about 1 nautical mile. And the bank angle required is somewhere between about 27 and 30 degrees. So we'll make some small adjustments, understanding that nothing's perfect. Take one last look around to clear for traffic to get ready to make our turn. And in this case, since we're doing about 200 knots at this point, maybe a little slower at the turn point, we'll figure on adding 3, 4, 5 degrees to our bank angle. A lot of this is a bit by intuition. For those of you that already can fly these, you know that. A little practice and you understand how to make these smaller corrections once you get to the actual conditions. That not only includes your speed, but also for wind conditions, which we have a fairly significant wind to deal with. So initially, as we lose speed, we'll increase our bank angle 3 or 4 degrees, hold about a 15 or 16 degree bank angle at this point rather than our 12 degree bank angle. And we'll continue to bleed off a little speed while we hold this. Also note that we have now adjusted to tune in the ILS, no longer needing the VOR. We're in the turn portion. And as we make the turn, we will begin to intercept the localizer near the end of the turn if our bank angle has been done correctly. Notice here that we've got a little bit of a wind tending to push us out against the top of the teardrop, so that too requires a degree or two of extra bank angle. In that case, if the wind were in the opposite direction, which would be unusual, because that would potentially mean you had a tailwind on landing, you would shallow your bank angle. But typically in the middle of the turn, if you have a wind like we have now pushing us out towards the top of the teardrop, then we just want to increase our angle a little bit. And as we continue the turn, and now that our speed has slowed down, we can shallow out. We're actually a little below our target speed of 160. That was kind of an average speed, because of course as you continue through the approach procedure, you tend to decrease speed, and with changes of configuration for landing, that also will allow you to fly at a slightly slower speed. Notice here now as we make the turn, it looks like we're going to have a pretty good headwind, and we're holding about that 10-11 degree bank angle, which is about right for about 140 knots at this point with a fairly straight headwind. And we'll watch to intercept the localizer. Notice we're only about a degree off the localizer at this point. We made the turn, and it brought us pretty close to the exact intercept point, just a degree off, and we're going to have just a little bit of a crosswind component from the right that's going to make us need to keep ourselves a little to the left. Drop down to 20 degrees flaps as we continue to configure for landing, and we'll take one quick look at what we've just done. Overflew the VOR, flew outbound on the 083 degree radial. Our turning point was at 10 DME. There are some intersections shown on Plan G, which I believe do not exist any longer. These were not on the chart. Plan G, of course, along with FSX, stuck in time in 2004. Made our initial turn a little steeper because of our higher speed, shallowed out a little bit, rolled out just a degree or so off of the localizer, and here at this point we're nearly on the center line. So we'll continue our approach in. At this point it becomes a very straightforward ILS approach. Keep ourselves on the localizer, wait until we intercept the glide slope, and we can make the final landing configuration changes needed. Full flaps come down, and down come the gear, and we'll just fly it in from here. And notice if you see the flashing light, there's some inbound traffic coming in behind us. So we'll move over a little bit to line up with the localizer. Notice that we still have that little bit of a crosswind component that's pushing us to the right, so we got to keep moving over to the left to keep the needle centered. And you can see out there that we're lining up pretty nicely. Good visibility today, so minimums really are not an issue. Nonetheless, we'd be pretty much in the right spot even if the visibility was poor. Final checks in preparation for landing, and nudge it over just a little bit for that good alignment, and we'll proceed with the final approach and landing. Still note the bit of crosswind here. It's pushed us off to the right a little bit. Move it over. Visual portion of the approach at this point, and we'll bring it on down. And as you notice, this is a contaminated runway. I guess it would be qualified as. There appears to be snow on the runway, so we'll want to be careful and not get too excited on the braking. Reverse thrust comes on. That goes off at 60 knots to avoid sucking anything bad into the engines. Not a lot of excitement on the steering or the braking, as I said, because you can see the snow on the runway, and out there is the inbound traffic coming back in, so we'll kind of watch him come in. Here it is. This is a view from right outside his aircraft. This is a special camera view modification so that you can see aircraft from their perspective, not from yours. And as he makes the turn and lines up, he'll come right in. This aircraft actually did a little bit of a different approach than what we did. Flew outbound as prescribed from the VOR, flew the 083 degree radial outbound, made the initial portion of the teardrop turn as usual, but his technique is to actually get about 2/3 of the way through the turn and then turn to a heading at a standard turn rate of approximately 30 degrees to intercept the localizer. This is actually a completely acceptable technique and preferred by some for any situation, and sometimes when the wind is giving you trouble, it may be a better technique than the one we did, trying to come right in directly. And here he comes down for his final approach. There we are sitting at the end of the runway, as you can see on Plan G. Again, the technique there just a little bit different than ours. Instead of trying to hit the teardrop turn perfectly, he did about 2/3 of the way through, did a steep into a standard bank turn to about a 30 degree intercept the localizer and landed. And he, on his rollout, also nicely on the center line, it looks like. And again, you can see the contaminated runway there. So back in our aircraft, we'll take one last look at the approach plate. I did put a link to this plate if you want to see it a little more up close and personal. We calculated the width across the turn, our turn diameter, if you will, to get our actual turn radius based on the distance out to the turn point and the 20 degree angle that we had to cross. Calculated our bank angle, made adjustments for our actual airspeed as we entered the turn, as well as the changes through the turn, plus the winds. And from that point, it's pretty much a standard ILS approach once we intercepted. Thanks for watching. See the email in the description here if you are interested in flying with us for these kinds of approaches or want to learn more. Thanks very much.